The universe, vast and glittering, may hide entire realms our instruments cannot see, challenging our sense of scale and reality. The story begins with the Big Bang, a sudden burst that created space, time, and the first particles, setting the stage for billions of years of evolution. After that prime moment, matter cooled, and gravity sculpted clouds of gas into stars and galaxies, tracing the large-scale cosmic patterns. Those luminous objects map only a fraction of the universe. Much of cosmic content remains invisible to telescopes that collect photons. Astronomers first guessed something was missing when galaxy rotations and cluster dynamics refused to match the mass we could account for. This discrepancy led to the concept of dark matter, an unseen substance that exerts gravitational pull without emitting or absorbing light. For decades, detectors and clever experiments have sought candidate particles, but direct detection of dark matter remains elusive. The lack of a clear signal forces theorists to imagine new particle types, weakly interacting sectors, or modifications to gravity on cosmic scales. Some models propose that dark matter can clump and form ghostly galaxies overlapping ours, massive enough to bend the paths of stars. These hypothetical dark galaxies would be invisible yet betray themselves by gravitational effects on nearby visible matter and lensing. Other hypotheses suggest mirror matter, a hidden sector of twins to familiar particles that interact only weakly with our forces. In such a mirror world, every electron, proton, and atom might have a counterpart, forming matter that rarely collides with ours but still curves space-time. Mirror universes, if real, could host their own astrophysics, stars, and potentially complex chemistry, all unseen by our eyes and telescopes. Physicists also consider extra dimensions, either compact and tiny or extended, which could alter the effective behavior of gravity. If additional dimensions couple to our universe, they might leak energy across realms or change how gravity weakens with distance, producing subtle effects. String theory offers a mathematical framework where tiny vibrating strings require more spatial dimensions to be consistent. Although string theory is not experimentally proven, it provides tools to explore how hidden dimensions and sectors could exist alongside our world. Quantum mechanics adds another layer of mystery. Particles can occupy multiple states and do not reveal definite properties until observed. Some interpretations suggest branches of reality that coexist but remain inaccessible until an observation collapses them into one outcome. This raises a deep question. Does observability define existence, or might vast structures persist independent of whether we measure them? Modern telescopes extend our senses by capturing photons across wavelengths, from radio to infrared, reaching back to the earliest epochs. Yet instruments that only collect light cannot directly measure mass that emits no radiation, so indirect methods become crucial. Detecting invisible matter requires careful study of motion, lensing, and the statistical distribution of galaxies across space and time. Gravitational lensing, for example, bends starlight in ways that reveal mass where no luminous object is seen, mapping the unseen scaffolding. Gravitational waves open another window. These ripples travel through matter and darkness alike, carrying signatures of massive events. If unseen structures merge or collapse, the gravitational wave patterns they produce might disclose their hidden properties and scales. Underground laboratories shield detectors from cosmic ray noise, allowing scientists to hunt rare interactions that could hint at new particles. Particle colliders and space observatories complement these efforts by searching for unexplained energy bursts, decays, or anomalous signals. Together, multiple observational strategies form a thorough hunt for the universe's missing components and hidden sectors. Dark energy complicates the cosmic picture further, accelerating expansion in a way that defies simple explanation and hints at new physics. Some researchers speculate dark energy could reflect hidden fields, interactions with extra dimensions, or novel vacuum properties. Each new measurement refines theoretical models, eliminating some possibilities while highlighting subtler, more plausible ones for the unseen. If unseen worlds truly exist, the universe we know might be only a thin slice of a far larger reality. The next question is, how close are we to discovering them? Scientists have built instruments so sensitive that even the faintest cosmic signals could be detected. Some are placed deep underground to avoid interference from Earth's natural radiation, awaiting rare particle interactions. When a particle collides with an atom, it can produce a tiny flash of light, a fleeting message from the unseen. So far, such signals remain extremely difficult to detect, but each experiment improves precision. In space, satellites like the Fermi Telescope and massive facilities on Earth, like the Large Hadron Collider, hunt clues at the largest and smallest scales. They look for unusual patterns, strange bursts of energy, particle collisions out of the ordinary, or distortions of light that could reveal hidden structures. The deeper we probe, the more we realize that invisible does not mean non-existent. It might simply mean not yet understood. Some theories propose that unseen worlds are not made of dark matter alone, but of mirror matter, twin particles of the familiar ones. In this view, each particle in our universe could have a mirror counterpart, moving invisibly yet affecting us through gravity. If mirror universes exist, they might host stars, planets, and even life, shadow worlds parallel to our own. Though strange, these ideas stem from fundamental physics principles about symmetry. The laws of nature appear balanced: light and dark, matter and antimatter, seen and hidden. Mirror universe hypotheses extend this balance into unseen realms. Meanwhile, gravitational waves, first detected in 2015, offer a new way to sense the invisible. Ripples in space-time travel through both matter and darkness, carrying information about massive cosmic events. If an unseen structure merges or collapses, the resulting waves may reveal its hidden properties. Some researchers suspect invisible worlds could explain why the universe's expansion is accelerating, the phenomenon known as dark energy. Dark energy seems to push galaxies apart faster over time, yet its cause remains unknown. Perhaps it is not energy at all, but the effect of hidden dimensions interacting with ours. If extra dimensions exist, the universe could be far more interconnected than we imagine, with unseen currents flowing between worlds. In some models, these dimensions act like cosmic membranes, sometimes touching or overlapping, exchanging energy and matter in ways we might one day measure. Each telescope, detector, or theory brings us closer to determining whether invisible worlds are fiction or reality. There is irony in the quest. The more we discover, the more questions arise. Every breakthrough opens doors to deeper mysteries. Even if we never see an invisible world directly, its effects are undeniable, shaping galaxies, guiding cosmic expansion, and driving human curiosity. For scientists, curiosity is the greatest force of all. It pushes us beyond observation, challenging imagination to grasp realities unseen. Perhaps imagination itself is the bridge, humanity's only tool to reach invisible worlds before science proves them. After all, every major discovery began as an idea, a question, or a dream that once seemed impossible. Invisible worlds may not wait to be found, but to be understood through advancing technology and human thought. Generations of telescopes in the 2030s may finally capture indirect evidence. Subtle changes in starlight, faint gravitational distortions, or invisible radiation patterns. When that day comes, we could map the hidden universe, revealing the true richness and scale of the cosmos. And when it happens, it will transform not only astronomy, but humanity's understanding of its place in the cosmos forever. Until then, we keep looking, asking, and imagining, because the greatest secrets of the universe might not be hidden from us, but waiting for us to be ready to see.